Blockchain, a distributed, tamper-resistant ledger. Agenda: Distributed systems trust models. Blockchain history. Why blockchain? Block lifecycle. Getting started. Basic workflow, consensus, and mining. Distributed systems trust. A distributed ledger lets many independent parties agree on a shared record of transactions without trusting any single party to keep it honest. If one participant tries to alter history, the rest of the network can detect and reject that change. Almost every application that needs multiple untrusting parties to agree on shared state eventually runs into this trust problem. Any system moving value or recording ownership between strangers benefits from a ledger nobody can unilaterally rewrite. Trusting a single central party to honestly keep everyone's records doesn't work once no one fully trusts that party. Centralized and distributed ledgers. A centralized ledger is maintained by one trusted party who can, in principle, alter or delete any record. A blockchain distributes the ledger across many independent nodes, each holding a full copy verified against the others. Centralized. A bank's internal database, one company's server, one party controls history. Distributed. Bitcoin, Ethereum, many nodes verify each other. Problems with centralized ledgers. Single point of failure. If the central party's records are lost, altered, or compromised, there is no independent copy to check against. Participants must simply trust the central party's honesty with no way to independently verify the full history. Auditing requires cooperation from the party being audited, who controls access to the records. A single database, once breached, can have its entire history rewritten undetected. Cross-organization transactions require a trusted intermediary neither party fully controls, misses out on a tamper-evident history that many independent parties can verify without trusting each other. The blockchain system. Transactions are broadcast to a network of nodes, each independently validating them against the network's rules. Valid transactions are grouped into blocks, each cryptographically linked to the block before it. A consensus mechanism, like proof of work or proof of stake, determines which node adds the next block, and the rest of the network verifies it. Other well-known blockchain platforms: Bitcoin, Ethereum, Hyperledger Fabric. Blockchain advantages: tamper-evident. Altering a past block breaks every hash link after it, making changes obvious. No single point of failure. The ledger survives even if many individual nodes go offline. Transparent. Anyone running a node can independently verify the full transaction history. Removes the need for a single trusted intermediary between untrusting parties. Smart contracts. On platforms like Ethereum, let agreements execute automatically once conditions are met. A large, active ecosystem of tools, wallets, and platforms has grown around the technology. Everything is hash linked almost. One huge benefit is that in a blockchain, almost every block is cryptographically linked to the one before it. Each block's header includes the hash of the previous block, chaining the entire history together. Changing any past transaction changes that block's hash, which breaks every subsequent link in the chain. This makes tampering with history obvious to any node checking the chain rather than silently possible. The chain of hashes is what turns a simple list of blocks into a tamper-evident append-only ledger. Blocks and hashes. Block: a batch of transactions plus a reference to the previous block. Hash: a fixed length fingerprint that changes completely if the input changes. A simplified block: every block bundles its transactions with the reference to the block before it. A simple proof of work check: mining searches for a nouns whose block hash meets a required difficulty target. History: the core ideas, hash chaining, and timestamped records were described in academic papers as early as 1991. Blockchain, as most people know it today, was introduced in Bitcoin 2008 white paper published under the pseudonym Satoshi Nakamoto. Bitcoin's network went live in January 2009, processing the first ever blockchain transactions. Ethereum launched in 2015, adding programmable smart contracts on top of the same underlying blockchain model. The technology has since expanded well beyond currency into supply chain tracking, digital identity, and enterprise record keeping. Why blockchain? Trust minimization. Participants don't need to trust a single central party. Tamper evidence. Altering history is immediately detectable by any node. Transparency. Anyone can independently verify the full transaction history. Resilience. The network keeps operating even if individual nodes fail. Programmability: smart contracts automate agreements without intermediaries. A large, active global community continues to build tools and applications on the technology. The Merkle tree. A Merkle tree hashes transactions together in pairs up to a single root hash stored in the block header. Lets a node prove a specific transaction is included in a block without downloading every transaction. Any change to a single transaction changes its leaf hash, which cascades up and changes the root. Never assume two blocks with the same Merkle root contain different transactions. The root uniquely represents its full set. Blockchain lifecycle. Broadcast to network, transaction, check against rules, validate. Consensus selects block, propose. Add to the chain, append. A transaction is broadcast, validated against network rules, proposed as part of a new block through consensus, and finally appended to the chain. Getting started with blockchain. This leads us to the three steps that get your first transaction sent. Choose a platform. Pick a blockchain that fits your use case, like Ethereum or Hyperledger. Set up a wallet or node. Create a wallet or run a node to interact with the network directly. Submit a transaction. Send a transaction and watch it get confirmed. Basic workflow. Blockchain. Each next node keeping hash reference of the first node. Trust in transactions. Submitting, validating, and confirming. Some call submit, validate, and confirm blockchain's everyday loop. A transaction is broadcast to the network and checked against the platform's validation rules. Consensus determines which node's proposed block gets added next, and the rest of the network verifies it. Confirmations accumulate as more blocks are added on top, making earlier transactions increasingly hard to reverse. Smart contracts can execute automatically as part of transaction validation on supporting platforms. Supports many workflows, payments, supply chain tracking, digital identity, decentralized applications. Works the same whether you are running a full node or interacting through a lighter client. Any questions? Thank you.